Welcome to season 11 of the Prosthetics and Orthotics podcast. This is where we chat with experts in the field, patients who use these devices, physical therapists, and the vendors who make it all happen. Our goal is to share stories, tips, and insights that ultimately help our patients get the best possible outcomes. Tune in and join the conversation. We are thrilled you're here and hope it is the highlight of your day.
Hello, everyone. My name is Joris Peels, and this is another episode of the Prosthetics and Orthotics podcast with Brent Wright. How you doing, Brent?
Hey, Joris. I'm doing well. I heard, though, that there was a little bit of an adventure yesterday, like 3dprint.com, was doing so many podcasts around Spain that it just shut down pretty much all the countries, including Spain and the neighboring countries, for a little bit yesterday. So tell me a little bit about that.
No, there was just no internet for like 7 hours and no power for 7 hours. And then that also affected some mobile phone networks. So we had like no mobile, no intermittent regular phones for some people. And then there was like no internet, no power for like 7 hours. So it was nice. It was actually, I think, this kind of thing, of course, becomes very problematic, if it's 2-3 days or something, but for just a kind of a long afternoon, it was actually pretty doable. It was nice. And I missed a lot of work stuff. So that was annoying. But had to reschedule a bunch of stuff. So, but it was nice. It was kind of like it was end of term school year kind of a vibe, and everybody clapped when the power came back on. So it was all right.
Well,
it was all right.
It's interesting to see what the news does. And then I've got some other friends in Spain too, and they're like, I mean, yes, it was not a great thing to have no power and all that stuff, but it was like everybody knew that it was going to come back on, and it was at least from some of the stuff that I saw. Now, it wouldn't have been fun to be on a train in a tunnel somewhere, that's for sure. But I mean, there was a lot of people out and about doing things and really taking it all in. So, but to your point, I can understand, like, if this goes on for days and days, that would not be a good situation.
Totally. So it was good for now. And for a lot of people, it's like a little mini internet detox, And I know like 3 or 4 people that I know that started books. I started reading a book I've had for ages. So it's actually really good. We should do it maybe once a week or something.
They just shut down the whole country.
Yeah, exactly. Shut down the country.
Yeah.
No internet.
Yeah. Okay.
Oh. Okay. So tell us, Brent, who's on the podcast today?
Well, I am super excited to have the next guest on the podcast. I would say this person is single-handedly the person that got me into powder bed fusion, not only design, thinking, and that is David Pierick. A lot of people know David Pierick. In the industry, he's been around for a while. He is recently retired, and he is a thermoplastics specialist, engineer, and he worked for a myriad of companies. And so we'll get into that journey a little bit, but we met when he was working at HP, and really, I would say it's because of him that HP is so ingrained into the prosthetic and orthotic industry. And I know that he has helped me out immensely on the journey to really create these sockets that are not only beautiful, but functional, and thinking about how design and function and elegance kind of all have to play together for a good patient outcome. So I'm really excited to have him on.
Awesome. So welcome to the show, David.
Oh, thank you very much. I appreciate the opportunity to come and talk a little bit. Now that I'm retired, if someone asks you to talk, it's pretty easy to say yes and remember all the great times that you had developing stuff.
Yeah, cool, man. So you did a lot of different things, but like here we're more kind of in the O&P stuff. So how did you end up getting involved with O&P? Is it just a coincidence? Did you guys think it was a great application? How'd you get involved?
Well, they had put some marketing studies together at HP and then at AMUG, and I remember this very distinctly, and I actually remember the room. It was one evening, I believe it was Monday or Tuesday night, and some of the HP people introduced me to Brent, and Brent told me his story and specifically talked about some of the stuff he was doing with South America, Guatemala, and some of his success stories. And I became completely fascinated with the ability to help people that maybe don't have the money or capability of helping themselves in terms of O&P products, mostly sockets. And so I looked into it a little bit more. And then, we always talked about wanting to be the leaders in O&P and trying to figure out why people weren't adopting it. And I ended up, there was the AOPA show in San Diego. I can't remember whether it was 2019 time frame, and convinced us to have a booth there. And we were the only ones there. We were the only additive manufacturing company there. And I saw all the parts that could have been printed and tried to figure out why they weren't printed. And that just kind of lit a fire under me to try to figure it out and work with Brent and take his leadership in that field. And I think we came up with some good solutions.
And if we look at this situation originally, the status quo, if you will, why weren't parts getting printed? We knew there were some people out there that invented stuff. They're making prototypes. But why were the majority of these IMP parts not being printed? Was it just like the people weren't familiar with the technology, or what was it?
Well, and this is my opinion, so when I looked at it, I think the first thing was that there just weren't enough people doing it, like Brent, that believed in it. And so I think the innovators and the leaders in the area said, hey, this is possible. But what was missing, initially what was missing was, hey, is it just as good as what they're currently using? How do we know that? And one of the things we found out was the current sockets weren't really being tested to rigorous standards. So I came from the aerospace field, and there you might test things for 5-10 years before you actually use it. And what I saw in the O&P was that it was, well, this is the way we've been doing it, and it works. And so trying to find a way to qualify the sockets and the different components so that we know that they would perform was a little bit difficult. We had to find some test procedures, and we had to find some ways to prove that printing was just as good. And so that was the first step. But even after we showed that, hey, this HP socket looks pretty good, it looks just as strong, it's more comfortable, then it was, okay, why aren't people adopting this? And we felt that it was because of the workflow. People didn't know how to scan, didn't know how to design for additive, and then didn't know how to print. So it wasn't just the printing, but it was the entire workflow. So two people that are very near and dear to my heart are Justin Hopkins and Dustin Klumpkin. And I asked them to spend the next year investigating it, understanding the different techniques, who was being successful with it, who wasn't, and then go on a kind of a tour and start presenting their findings. Not that we have the solution, but here are the challenges and here are the potential solutions, and bringing awareness to it. And so I think that was the second thing. So first of all, it was, does this work? And then secondly, it was, what is the workflow? And can we figure that workflow out?
And how did you test these things? Because that's actually a pretty tricky thing to do. And initially, how were you able to get that data? Was it just, how did you do that?
Well, it started off with orthotics for footwear. And there was a study done in Spain, and we took that and developed that and worked with the University of Toronto. There is maybe the world's leading expert in orthotics, and we worked with that group to develop a test method to compare the durability and strength of additively manufactured orthotics compared to the standard process with polypropylene. Now, I knew that the polypropylene used for the current orthotics, I knew that material characteristics, and so we chose a material that we felt would be either the same or superior to that, and then developed a test method. And the first couple of times we did it, it showed some possibility, but we didn't fully believe everything that we were testing, so we refined those test procedures. And then once we did that, then we started looking at sockets, and we worked with University of Colorado Colorado State, I'm sorry, to develop some test methods.
Okay, cool. And subsequently, okay, so now do you then offer, do you then seek out certain people to work with? And what kind of people do you seek out to work with initially, get those first parts out when you have that data?
Yeah, and Brent was a major helper here in terms of identifying what kind of products, what kind of sockets that we should be testing. We're not experts in orthotics or prosthetics. In fact, know very, very little about that. So we rely on the experts to help us choose real test methods which replicate real methods or real life. And then we do it the best we can. So, we test for strength and then we test for durability. And we try to mimic real life. I know the first time we tried to test for strength, we actually bent, I remember this, we actually bent the 1-inch aluminum rod before we bent the socket, before the socket deformed. And I think that was more of a design of the test equipment. But it was kind of eye-opening, too, about the strength of these printed parts.
Yeah, and I think the other thing that's interesting about all this is, and what I appreciate about the side that Dave really worked on was the testing and the physical nature of it. But I think the other part that gets looked over sometimes is the aspect of the data that we get from the patient. Now, that it is considered subjective, sometimes objective, and we call it the patient comfort score. So are you more comfortable in this socket compared to the other socket? And over, we saw that people were more comfortable in a PA12 socket, and then the comfort even increased with a PA12 with a flexible interliner that goes inside. And so what's neat is a lot of that studying can be done, or testing can be done in parallel, along with these patients wearing it, and then with fitness trackers too. And so I'll never forget, and we've had him on the podcast, Richard Blaylock, who ran a marathon. I mean, he literally had over 3 million marathon cycles on his multi-jet fusion socket, from running. And so with that, we were very confident in what powder bed fusion can do. And the other interesting part of the testing that David did was, because it was creating failures in the actual components and not the socket itself, they also did some testing on what were the circumstances that a socket did fail. And so there were some pretty intense moments that happened in that testing, which is when any socket fails. And I rarely hear of a socket, and I think this is important. I rarely hear of a socket that fails just when somebody's walking. There's always some sort of event that happens to create a failure. And that's the stuff that's hard to design for and around. So anyway, I just wanted to say that those two paths, not only patient information, but then the engineering and strength side, are very critical to saying, yes, powder bed fusion not only is a lateral move from traditional fabrication, but could potentially give you better outcomes.
Yeah, and I would say that's what inspired us is Brent. Your comments about the patient outcomes. Your designs and the patient having better outcomes, a better life because of that is what inspired us. And we saw that, hey, and I'll be honest, we made a conscious decision that we may not make a lot of money. The company may not make a lot of money in O&P, but it's the right thing to do. These patient outcomes are so far superior, at least from what you had showed us, so far superior to their current product that we have to do this. We have to figure out how to get this into more people's hands so that they can experience the better outcome and have a better life because of that. And so, we can't, as engineers, we were not able to understand that patient outcome and the how it affected their lives. But what we could do is overcome some of the challenges, the factual challenges of, is this really going to work? And Brent, you did show us a couple of times where parts had failed after several years of service, and we took those parts and we analyzed them, and we tried to figure out what potentially caused those failures. And it came down to some little things like radius on edges to improve that, occlusions that we need to be a little bit more careful about the material we use. And I know you've solved those problems. So we worked in conjunction with you, and there was never a thought that, hey, we can do this automatically. It was always the thought that we need the experts to guide us on what to do, the O&P experts to guide us on what to do and how to test and how to do our part to support the business.
Super cool. And if you're looking at doing this parts testing, right, real world parts under simulated conditions, do you have any general advice on doing that? Besides finding a university, I think that was your thing. Do you have any general idea on how to do that and how to make that more successful? Because I think that's something we would encourage more people to do.
Yeah, there's some standards now. In fact, we found a standard. I can't remember whether it was an ASTM standard or an ISO standard or an O&P standard that we kind of copied. And then, Dustin Klumpkin, Justin Hopkins at HP led some of this testing. They would be a great resource to identify which tests to run. And of course, Brent and Dustin, I believe, made a presentation. I don't remember which conference you made a presentation at, Brent, but showed some of the results and the testing procedures.
It's a little while. I mean, it was very early on for that one, but that was a great one. And hopefully, I would say it was either an Academy or AOPA meeting that I happened at, that it would be a good one for people to revisit for sure.
Yeah, and I know at the time we were requesting feedback from the experts. Hey, what did we do right? What do we need to improve to make this better testing, more like real life? And it comes down to what is the peak strength of the component. So you do a short-term compression or tensile test, and then what happens if you're using this 1,000 times a day? And then cycling under the loads that you expect to see when someone's walking. And so that's what we did. We did both cycling as well as ultimate strength.
And then we also, like orientation, for example, and there's a bunch of other factors that have a really big effect on that. Did you look a lot at orienting parts and other kind of things like that?
We looked specifically in orthotics, we looked at print orientation relative to fatigue life and strength. And we found some things there that, if I recall correctly, it was better to orient in the vertical direction that gave you a little bit more, the horizontal direction, which gave you a little bit more fatigue life. So there are tips and tricks that we have. I mentioned earlier about the radius of any parts that might see cyclic fatigue is extremely important, and no sharp edges, anything in the design itself.
I think that's super important for our listeners to take into consideration, especially when they're looking at any of the powder bed stuff. Is you see a lot of the extra embossed patterns and diamonds and lattice structures and all that stuff for specifically PA12, but PA11 too is all those areas really, unless they're nice radii, they can become design issues and failure areas. And so my encouragement to people is really, when you're designing these things, you want them to flow very nicely. No, like what David said, is no hard edges, no 90-degree turns with an edge. You always want to radius. And then if you need some areas that are thicker or thinner, the tendency is just to throw a rib or some sort of corrugation there. But what we found is that if you do that and you don't transition that corrugation to the actual surface itself, that also can present stress riser challenges. And so my encouragement to anybody that is looking to get into powder bed fusion is really don't don't guess. Is find some people that have gone before you, and I'm still learning with all this stuff, but I've failed a lot too. But there's plenty of other people that have done some really cool things that I'm sure would be happy to share some design guidelines. But my biggest thing is, especially with this powder bed fusion push, and there's a lot more people using it. I mean, when you go to, say, an OT World, or even the Formnext. I mean, yours, when you were in Formnext, they had a ton of prosthetic stuff. It's definitely a great way to use additive manufacturing. And we're at this kind of inflection point of, we want to be successful, and we need to keep on building that momentum. And failures can hinder the momentum, especially when it's not something that's your primary way of designing. So my biggest encouragement is, find somebody that has gone before you, and line up with some smart people like Justin, like Dustin, that can give you some insight into design criteria for really any of the powder bed fusion sockets.
Yeah, I think that's a great comment. If you go and say, I'm going to go print something, and you try to do it by yourself, you're going to have failures, and you're going to be soured on the technology. Use someone like Brent to design an appropriate socket or an appropriate component, someone that has done it for 7, 8 years now, 9 years, and learn from them so that you don't have failures at the beginning. And then take it on yourself after you have some experience and after you have some success.
Yeah, and if you look at before this, if you're, do you have any more general advice on just understanding applications, understanding that market? So first, you did the parts testing, you listened to these expert users, and how do you get it to the next level where you kind of like take it from these experts and take it to the bigger group?
Yeah, and I think that's building confidence in it, right? So at the first, when we first looked at this, we said, okay, is this really a better technology? Is it something that can compete? And what are the challenges? And one of the challenges was the market itself is very fragmented. It's not one large company doing all of the sockets. Like automobiles. There's the big three in the United States, and you pretty much work with them. If you can convince one of them to use your technology, they're going to use it, and you're going to be a great success. But in O&P, there's a lot of shops around the country, hundreds of shops, and each one of those shops needs to learn how to do this process. So how do you address a fragmented market, a segmented market, where there's many low volume, high mix components? And so there's some education that needs to happen. There's awareness that all had to happen. And so what we did was we said, hey, look, our part of this is just to do the best job we can to prove out that the technology works from a functional standpoint. And then as we learn stuff, as we learn about failures, as we learn about improvements, try to incorporate that and build a credibility in that field that allows more people to accept the technology. So our goal wasn't necessarily to say, hey, we want MJF to be the leader and the only one that prints this. What we wanted is success with additive manufacturing. And that's why we tended to share everything that we had with the industry as well as with our competitors. And if you look at what some of HP's competitors are doing, I think it's fantastic. Our job, we didn't look at our job as making HP the only one. We looked at it as saying, hey, let's have the industry adopt additive manufacturing. And I still think that's the right approach. It's a very large pie. Everyone can have their place in that piece of that pie. So let's grow the industry, not be competitors and limit the industry.
So we're seeing a lot of adoption now in sockets, test sockets, and sockets more broadly. What are the other parts where you think that the really O&P could really profit from this, from additive?
That's a good question, and the answer is yes, to take our learnings from sockets and orthotics and apply that to different components. I think one of the things, if you're thinking about maybe automated fingers and there's so much in microelectronics that the printing part is minor relative to everything else. You print a part that goes on electronics for a replacement hand, but in a socket's functional. It's the major component of what you're trying to do. And I think that's what you need to look for. Where can additive be the major part of the component or of the solution? And sockets is one of them. Bracing, casting, where you might want a perfect fit, a custom fit might be another area. And then anything that requires mass customization is a good opportunity.
Yeah, and of course, well, first it was the name of the game was PA12, and now we've got like more PA11. We've got different materials. And how do you feel about those? Like, you know, polyprop as well. How do you feel about those different materials for MGF in particular, or maybe additive more broadly?
I think all materials work in the right application. My experience has been that the PA12 was the original one. It's a great product. If we compare that to PA11, PA12 is a little bit stiffer. I think it's a little less comfort. The PA11 looks a little bit better, tends to have better fatigue properties, and it's a little bit more forgiving, although it has a little bit higher strength versus stiffness. So it's a little bit less stiff, but higher strength. And, you know, I think my personal opinion is that PA11's, you know, a little bit superior to the PA12, but it's not used as much. And it's also more expensive too. So you have to consider that. Polypropylene, I think, is an industry standard in orthotics. Because it's a new product, I'm not as convinced that it's as robust as the PA11. But I think it's a very good product.
Meanwhile, if we look at especially the material extrusion space, they're using a lot of TPU. And now there's also new TPA, TPE, other TPU variants and stuff like that. How do you look at that? Because that is looked by a lot of people as a really interesting material. It's very heavy, though. It's but it does totally seem to have its niches, right?
Yeah, definitely. You know, for the TPA and TPU and TPE materials, certainly anything where cushioning, energy management, you know, for helmets, cushioning for prosthetics. You know, people talk a lot about one of the material properties being the shore hardness of the material. And in the past, and I've worked in TPUs and TPAs for maybe 15 years in previous lives, and we always tried to achieve a certain compression set with a certain shore hardness. And we always wanted to drive the hardness down. Shore 65, shore 55, shore 45, and try to drive that down while keeping the compression set. The compression set is basically the value that when you squeeze something, does it return all the way? And you want it to return all the way. So we had this balance, and we only had the molecules to adjust with injection molding and with thermoforming. And so what we'd try to do is adjust the shore A hardness. And voila, I got exposed to printing lattice structures in TPUs. And here's a way to take a fairly hard TPU, maybe a shore A 70, 85, or 90, and soften the feel by creating these rib structures or lattice structures. And to me, it just amazes me that this is an opportunity for us and what we can do with that if we have the right lattice structure. So in that particular instance with a TPA and TPU, it's a combination of the process and the material. You have a material that forgives, doesn't crack, but has some good resilience. And being able to make a product that is resilient, gives energy return, but also softens is quite incredible. There's a new material out, not necessarily for MJF, but for powder bed fusion for SLS machines, and that's called PK5000, which Jabil introduced to me, and now I think it's Loomis Polymers. Is that correct, Brent? Loomis has taken over the PK5000 in the U.S.?
That's correct. Yep.
Yeah. And in terms of the future, I think that PK5000 is a real winner. Everything that I've seen would indicate that it has the stiffness of a nylon and the softness of a TPU. And I think it's going to be a great product for the OMP. And Brent, you probably, at this point, you probably have more experience with that. And you and I probably haven't talked about that for maybe 8 or 9 months. Have you seen any good things or bad things about the PK5000 that we haven't talked about?
Whew, boy. So other than learning a new technology, SLS, we've been running the PK5000. Actually, I mean, we've been testing it for almost, I guess, 2 years now, and we've been very pleased. Our patients have been very pleased with it. And I think what's interesting is that it opens up other possibilities because of the impact resistance and the failure modes. So a lot of the adjustable sockets can then be made a little bit thinner than compared to, say, a PA11 or PA12. So those are the things that we are seeing. One of the things that is important in this, though, is we are definitely testing how thin can we go, and then when we're that thin, what are the fatigue properties of the material? And so those two things have been an interesting thing, and we're very positive. But it's one more aspect of how critical the design is to have success. And so, just like what you said, there's a myriad of ways to have success, whether it's PA11, PA12, the PK, the TPU, a polyprop, but they all have their personalities as well. And so, learning that is difficult.
So maybe on the PK5000, great product once you can figure out the tips and tricks to actually print it. Is that a good
Yeah,
show?
kind of like what you were saying when you were talking about HP and the prosthetic and orthotic market. One of the reasons was it wasn't to make a lot of money, but it was to make a difference in patients' lives. And it's for lack of a better term, like a little bit of a labor of love. And I would say that in the same way, we are really, really thrilled about the properties of PK5000, but the learning the technology of the SLS, but then also learning the printing characteristics of it, because it is more difficult to print than a PA11 or PA12. And the way that I would equate that is, if you're in FDM, it's a lot harder to print peak than it is PLA. And you're going to have a lot of learnings, but once you dial in peak, then you're dialed in and you're good to go. And I would say that's kind of where we're at with the PK5000. We're having really great results. The patients love it, and now it's more of a, how do we optimize and get the most out of the characteristics of this material, because it does. The characteristics are so much different than, say, a PA11 or 12. In the same way, they're the same, but they're like the stiffness, some of the flexibility, all that you can use to your advantage in the PK.
Yeah, maybe I liken it to when we introduced PA11. We had PA12 and we introduced PA11. I certainly felt it was a better product, but we had a few issues that we had to overcome, and it took printing with it to overcome those issues. And now I would say there's probably very few differences between 11 and 12 in terms of printability. I was exposed to the PK5000 working in aerospace, and one of the tests we ran, two of the tests that we ran, one was tensile test under temperature. And even though the PK5000 feels softer, the tensile strength and flex strength of the PK5000 under temperature is actually better than nylon. And then the other test that really, really surprised me was we made containers, pressure vessels. We made some pressure vessels, and then we pumped those pressure vessels up until they burst. And one of the last designs, I believe it was at about 2 millimeters of thickness, we actually burst at a higher pressure than the aluminum replacement tank, the tank that we were replacing, which still surprises me. And there were some things there, but it was actually burst at a higher pressure than aluminum, welded aluminum. And that's quite surprising to me.
It is. I mean, I think that's what's neat about this, and I think that's what's neat about SLS. But it's also scary in the same sense because in the HP multi-jet fusion is a black box essentially. All the knobs and all that stuff. I mean, you might have a few like irradiance and that, but even like with the 5200, I think that's pretty much automatic, and you've got thermal cameras and all that stuff. So it's a set parameter that you're going to be successful. So you just think of SLS and you have every single knob under the sun that you can tweak, and it directly correlates to what the output is. And that is what makes SLS exciting and scary all in the same sentence.
Yeah, advantage and disadvantages to both. I mean, you can make the SLS the product you want, but you can also make the product you don't want, right? If you don't know the exact conditions that you want to print that at. Whereas with the, I guess, the certified process or the qualified process, you know that you have some consistency. It may not be optimum for your product, but it's a consistent value. You're going to get the same properties every time if you run it under the menu. So, yeah, maybe a little bit more development on that side to prove consistency of the product is maybe one.
I'm also a PK 5000 fanboy. I love what you guys haven't mentioned, by the way, is the moisture uptake. The surface quality, I think, is amazing for a lot of stuff, like gear knobs and stuff that flows and stuff. And also with pretty high refresh rates and a not super mega high price. It's like I used it for years as a niche material, and I would use it in a report and saying, well, PK 5000 is essentially the only kind of high performance material we have in additive that's actually low price. If you look at it, just the economics of running it with the refresh and on the machine, with the initial purchase price, mean that it's one of a kind, because we're used to having these like materials where they were like, it's like literally people were pitching stuff with like, it's $500 a kilo and we can't recycle any of it. It's like, and it's the highest performance material in the world. I'm like, you're kidding. Who's going to do this? And so I think the coolest thing about PK 5000, which I love the Brent is actually one of the people keeping it alive, is that this stuff is, incredible bang for the buck. There's nothing like it in bang for the buck.
Yeah, I agree. And so I've been in plastics for 38 years, have a couple of degrees in that area, and the material surprises me. It just surprises me in terms of its cost performance in a good way. And there are challenges. It's a new material. It's not widely used, and there's challenges. I just see a lot of potential there for that type of material.
Me too. But okay, let's talk about something else a little bit. We kind of touched on it before, but one of the things that's classically a good business case for additive is like complex assemblies. You mentioned it with his invention, these fingers and things like that. But we kind of seem to have kind of hit an imaginary wall where like some people are making like really intricate kind of fingers and maybe some joint type structures. But we know theoretically that especially if you use several different additive technology, you can go much further than that. We could print actuators, we could print little valves. You were talking about pressure vessels. You could also use those for kind of pneumatics. Is that just a lack of imagination that we're not going there? Because clearly we could be making like in a soft robotics way, but also in a kind of more pneumatics type of way, we could be making a lot of like, muscle type structures using additive as well.
Yeah. I laugh because I remember I'd 5 years, I'd give these presentations and I would tell them how great additive is and everyone should be doing it. And then someone would always ask, well, why aren't people adopting it faster? And at first it stumped me. And then I would just kind of say, well, you know what? It's because of people like me. Yeah. People that have been doing this for, plastics for 35 years, who are used to machining straight things and CNCing and injection molding. And you got to get rid of the people like me that can't think in 3D. So we need designers and we need people that understand and think in 3D. I think in 2D. I think of a surface. I think of a 2D surface, and how does this go to another 2D surface? How am I going to machine that? How am I going to injection mold? What's the draft angle? And you need people that don't have those geometric constraints already built into their mind, and it takes a little bit of time. One of the things, and Brent and I have talked about this, and several people, is that in retirement, I'm not making any money, but what I am doing is I put together an introduction to additive manufacturing course at the University of California, Merced. We're doing our second class. And last week I went up to, it's online, it's an online class. And I went up last week to meet the students, and they had a project. And that project was to design a crate or a contraption that will allow an egg to survive. Survive a drop, and it's a classic, fifth grade or high school type contest. But what we said is that you need to design a contraption that's less than 150 grams and will drop from 12 feet. So they did all the hand calcs. And the thing that amazed me on Friday was that there was 7 teams, 7 completely different designs. And I wish I could show them to you. There were designs where they were trying to slow the contraption down using parachutes and propellers. And there's other people that were doing out of a TPU material, just cushioning. And one that did one of the best is it was a TPU ball with a bunch of other TPU balls inside of that, and you squish the egg into the center of that ball. And that did really well. But another one that did really well was one that had propellers on it, and it had a nose cone with an infill that allowed the TPU to absorb the energy before the egg did. And so the reason I bring that up is that creativity could not have happened with someone like me, because I don't think in those terms. But these students, mechanical engineering students, that started off in January, didn't know anything about additive, didn't know there were 7 different types of additive processes, are now creating these designs that I couldn't come up with because I don't think that way. And it was just absolutely fascinating. There were 7 completely different ideas, from containers inside containers to lattice structures to things that look like rocket ships. One was called the Lunar Lander, which was fascinating. It had a combination of deceleration devices as well as impact energy management systems, and just fascinating, absolutely fascinating. So when you talk about this, I think what needs to happen is people need to come up with, younger people need to come up with this creativity that allows the thought process for geometric design complexity.
Oh, cool. And I think that will happen. And another interesting we kind of bring up as well is this whole idea of, if we're looking at like an integrated functionality thing, what we could also do, let's just keep to a socket, is we could make a structure very similar to a liner type of soft structure out of lattices or whatever. We could, make that socket structure. We could put in a shock absorber type of structure in there as well. We could, and we also see this, and do you believe in something like that going forward? Like, once these kids kind of get a couple of years in their career, are we going to see people come up with something like, out of one material, out of one printing technology, making something that has like so many different qualities to it because of that? They think in this integrated way.
Oh yeah, definitely. I see that happening. I see it's an evolution, right? And that's exciting. But that's why I like staying in additive, like why I'm teaching the classes, because things are happening so fast. Stuff that we taught last summer are out of date now. We have to teach it differently. So in terms of design, in terms of replacing silicone liners, people want to be able to design lattice structures that do a better job of supporting the impact energy associated with the bottom of a socket, right? So that the stump doesn't hurt. We want to do that. Well, what's the right design? I think we know. I don't think we know for sure. I think we try things because, you have to support someone that may be 100 pounds and someone that may be 250 pounds. Those are going to require different structures. Do you have an inch of package space or a half inch of package space? If it's only a half inch, what kind of design do I need to come up with that will support a 250 pound person, yet provide the deceleration on each step? I don't think we know that. And I think that if we could determine that and make it general use, it would become commonplace to design things like that. But I know Brent's designing structures that manage that impact, but I don't think he can go anywhere and say, I have a 250 pound person, and I have 1 inch of package space, and this person is only going to be walking, not running. How do I design that lattice structure? I think what Brent does is he takes a really good guess based on his experience, and we have to get past that. We have to understand the impact energy curves based on testing results.
Yeah, I'm glad you pointed that out because I'm trying to work on a number of different products, and some of them are in shock absorption kind of stuff or sports gear type of stuff. And we hit this every single time.
Yeah.
So I could be working in SLA for a handlebar, or I could be working in multi-jet fusion. Brent printed out some stuff for a multi-jet fusion kind of bike part. We're printing up other parts using material extrusion and TPU, just desktop printers. And every single time we hit a problem that we can't find someone to do kind of the force calculations, all this stuff,
Yep.
based upon that material and that structure. And to me, it's really interesting that some people do this. Like the Kupol is a company that does this. They do this. They do this for the light. What are they called? Light force or lightweight or whatever helmets for the NFL and stuff. And but there's very few people that specialize. But if there's one skill that I think either a software tool could teach us, or somebody could just rent out, it would be just to say, like, okay, how big is the NFL player? What are the impacts? And this is the structure that will manage that the best. Or, taking that and taking it also to tennis rackets or to sockets or to all sorts of stuff. I think that's really the missing link in a lot of additive stuff at the moment.
Yeah, and companies are working on it. Intop has some good software. I know HP has a group that works on just lattice structure energy management. I know EOS has one. Certainly Carbon in their helmet designs have some fantastic products. Carbon has a different proposition though. Theirs is energy absorption. So there's a difference between having a product that you want to return energy and one that absorbs energy. So for absorbing energy, something like a helmet, where there's a massive impact, you're going to want to use something that absorbs energy more than it returns it. But for something like the bottom of a socket, or a great example is a running shoe, you want that lattice structure to be cushioning, but also return as much energy as possible. And that's a different material, as well as a different lattice structure design. So it's very complex. And putting all of that together just hasn't happened yet. And someone needs to focus on that. And they need to focus on not just one process, but how do multiple processes solve the problem, based on SLS, Carbon, Clip, and MJF. How do you solve that problem? And it's not there yet. It's not there yet. And that's why I'm so excited about the industry, is because there's so much potential.
Yeah, exactly. And I think also on top of that, I think is what's interesting is, like, you're used to, for example, in the polymer world, just saw something in compounding maybe, or just the choice of your material, right? Well, here we can affect how that material works by changing some structures in the printer, for example, depending on what printer we use. We can do infill structures, or we could do differences in those structures. And then we could change the part, and we can change the texture. So they're on so many levels. Like for example, if you would want something to feel softer, okay, what do you do that? How do you do that? Right? You chose the material, or you make a better texture, or do you make it, So there's so many options that I think also people are also kind of like doing a lot of guesswork there, because we just don't really understand the feedback loops.
Yeah, and I, so I became fascinated in polymers when I was a young engineer, and one of the reasons I was so fascinated about it was that you can think you can know a polymer and how to make it work. But there's so much to learn. Every time you think you know something, life and experience teaches you something different. And that's one of the reasons I loved polymers, when I wanted to go into it. And one of the reasons I love additive is that you think you know it, and you do something, you say, this is going to work. And then you go, didn't work. I got to figure that out. And that's kind of where we're at with polymers and with lattice structures, energy cushioning versus energy absorption. And the process itself. So there's multiple variables. There's the process, there's material, there's design, and then there's application. And that's a very complicated matrix to understand. And I think you have to start and maybe someone with some polymer expert, someone with design expert, and physics expert working together to solve that problem.
And if you had some advice, somebody who wanted to take a deep dive in the polymer, make like polymer as their career or something, what would you do? Because it's really tempting to just specialize on one family, for example, or one type of material. It's really tempting to get stuck in like a world, like the sports world, and work for golf companies a lot. It's really tempting to get stuff on more of the scientific stuff, and then end up being kind of like more a lab focused person. What would you really advise people to do to really have access with or success in making polymers work for companies? Because I think that's really where if you're in the lab, you're going to be great in the lab. And it's wonderful, but you're going to stay there, right? And that's okay if you invent like the new whatever PEC Plus or whatever PEC 9000 series, whatever.
Yeah.
But if you're not that type of person, then that's probably not the place for you. And where I see a lot of the value is making polymers work for companies. So
yeah.
How would you advise a person in that case?
I think learn how to work with others. Learn how to team up with experts. I think that's if I was to say one thing that in the things that I was successful at, it was because I was able to work with experts in their area. People like Brent in the OMP area. I think of some of the people I worked in automotive, people I worked with in medical products. We designed a material, a polypropylene that is now used in about 90% of all the syringes. And I didn't lead that team from a position of expertise, but I was able to get the polymer experts with the applications experts, with the irradiation experts, with the testing experts, and we worked as a team. Because I think it's so complex that one person doesn't know everything. And so you have to figure out how to work with people, and you have to figure out how to build a consensus on what you should be doing. And so I tended to I always said that, I'm not very smart, but I work really hard, and I like working with people and trying to get them to do their best, for the goal of the project. And so, my recommendation is learn how to work with people, learn how to appreciate their skills, learn how to appreciate their experiences, even if it's different than your own, and use that to your advantage. And I think that's why I've been on some successful projects in the past 30 or 40 years.
Yeah, it totally sounds absolutely wonderful. And generally, I think, do you have any advice for people coming into this OMP world, kind of saying like, this is what you really should do? Is it also working with experts, or is it kind of like, was what I liked about your thing is we started with rigorous testing, whereas a lot of people in this, business seem to think it's more a bit of an art thing.
Yeah.
So do you have any more general OMP related advice there?
Well, yeah. For me, I don't know anything about OMP, but I had expertise in polymers and I had expertise in testing. 15 years testing for automotive, 10 years testing for aerospace, understanding different tests, fatigue, strength. That was my expertise, and brought that to people like Brent and the University of Calgary, Colorado State, and talked to them about my expertise and what I wanted to do, and gain knowledge from them, and partnered with them to get that knowledge and work together as a team. So, it's a lot of fun when you work as a team and try to figure out a solution.
Yeah, that's true. I'm increasingly finding that definitely additive is really very, very much of a team sport, let's say. So ideally, you should work with a lot of people. So, hey, David, thank you so much for being with us today.
Hey, I appreciate the opportunity. It's always nice to kind of pontificate about things that you've worked on.
Awesome. And Brent, thanks for being here as well, as always.
Well, yeah, this is great. And Dave, thanks for really inspiring a lot of people to move in this direction. And I think there's a couple takeaways. One is obviously we got into the weeds of the nitty gritty of the different materials. 2, the importance of education. And 3 is surrounding yourself with other people that are that know their domain well. And with that, you get good outcomes. And so I think those are really the 3 main things that I saw. And I think Dave embodies that very well.
Well, thank you very much for the opportunity.
All right. And thank you guys for listening to another edition of the Prosthetics and Orthotics podcast. Have a nice day.